Hi there. I've got one more video for section 7.5. I'm going to do another example of using the Laplace transform to solve a second order differential equation. And in the last example, in the last video, the problem we did, we could have solved using the techniques from chapter 4. And in this example, we're going to do one where the methods from chapter 4 don't apply because we have non-constant coefficients in this. So it's still a linear second order equation, but it's non-constant coefficient. So this is example 4 from the text. And we want to solve the initial value problem y double prime plus 2t times y prime minus 4y equals 1, and our initial conditions are y of 0 equals y prime of 0. They both equal 0. And so what I mean by non-constant coefficients, of course, is that we've got this 2t stuck in here. That means that everything we learned in chapter 4 doesn't work out for us. So we're going to do the same thing we did in the last video. We're going to let capital Y of S equal the Laplace transform of little y of t, and then take the Laplace transform of both sides. And that gives us that, switch to black, we get L of y double prime plus 2L T y prime minus 4, and now we can just write big Y of S equals the Laplace transform of 1 is 1 over S. Now remember the same thing we did in the last one. If we were to consult our table of properties, we knew that this equals S squared times capital Y of S minus S Y of 0 minus Y prime of 0. And that just, since these are both, since that and that both equal to 0, we've got S squared capital Y of S. And then this next term is a little bit trickier, so let's take that and work over here. Let's pull up our properties table again, and if we've got, we'll take n equals 1 over here, and we know that Laplace transform of t y prime equals negative d ds L of y prime, and we know that L of y prime is equal to negative d ds, there we go, and then L of y prime using that relation up there gives us S times L of little y, but we're just going to call that big Y, minus Y of 0. Now we can actually take the derivative, and this guy is 0, and it would be 0 anyway once we took the derivative. And we can do product rule on this term here, so we get negative S times Y prime of S minus, because that negative is going to carry through, Y of S. So now I've gotten rid of the table, and I'm going to go back to the problem over here. Oops. And keep working, filling in what I've just done. So now we have, back down here, we get S squared times capital Y and I'll drop the s again, plus 2 negative sy prime minus y minus 4y equals 1 over s. So just like we did in the last problem in the last video, we'll get sort of all of our y's together. Well, we already have all of our y's together, but simplify things anyway. So we have negative 2 sy prime, and then all of the y terms, we get s squared minus 6y equals 1 over s. Now we'll divide by the negative 2s, and we get y prime plus 3 over s minus s over 2. That's what you get when you divide the stuff in the parentheses there by negative 2s times y equals negative 1 over 2s squared. Now, what we're left with is a new differential equation in capital Y, but fortunately this is a first order differential equation, and it's linear and we know how to solve it. So let's shrink up our workspace a little bit and think about how we solve this. So go back to chapter 2, whatever it was, and think about our integrating factor. Mu of s is going to equal e to the negative, or e to the integral of the stuff in front of the y term, so that's 3 over s minus s over 2 ds, which will equal e to the ln of s cubed minus s squared over 4, and that's going to equal s cubed times e to the negative s squared over 4. That's our integrating factor. So now we're going to do our trick of take our first order equation and we're going to multiply it by mu of s, and then that gives us our left hand side of the differential equation we can write as a single derivative. So then we get that d ds of mu of s times capital Y of s equals d ds of s cubed e to the negative s squared over 4 times y of s, and then it just equals the right hand side times mu of s, so that'll give us negative s over 2 times e to the negative s squared over 4. Now we integrate and solve for y, so the next thing we'll do here is integrate, and then we get s cubed e to the negative s squared over 4 y of s equals the integral of negative s over 2 e to the negative s squared over 4 ds. And I'm just going to tell you that this equals e to the negative s squared over 4 plus c. You could do, let's see, a u substitution on there. That one's pretty straightforward. And then the next step is going to be solve for capital Y, and that will give us capital Y of s equals 1 over s cubed plus some constant times e to the s squared over 4 over s cubed. Okay, so the next thing we have to do is take the inverse Laplace transform of y, of capital Y, so that we can get lowercase y. And that first term looks fine. The second term with the c is gross and bad. So what would be really nice is if it would just disappear, like if c were 0. And so here's where we're going to use a really handy-dandy fact about Laplace transforms. And so let's sort of make an aside over here. Let's make a fun fact. Let's see, I'm actually gonna put some caveats on this. Fun fact, if f of t is piecewise continuous on 0 to infinity and of exponential order, then the limit as s goes to infinity of L of f of s equals 0. And we've seen this, if you look at the table of Laplace transforms, then they all look like 1 over s and stuff like that that will vanish as s gets big. And we're not going to prove that. I'm not going to prove that right now. This is outlined in one of the exercises in section 7.3, and I'm just going to tell you right now that I love giving you proofs on exams, and this is probably a pretty good one to do. So I might be giving you a heads up on one of the exam problems, which would be, let's see, exercise 7.3, problem 26. So if you're paying attention to these videos, then I would suggest you go take a look at that one. Anyway, so now we're going to use that fact and go back over here. And if we apply that to this piece right here, as s goes to 0, if c was 1, if c is positive, then as s goes to infinity, this goes to infinity and so does this, but the top goes to infinity faster. And so this will go to infinity as s goes to infinity unless c equals 0. Okay, and if you don't believe me about this limit, if you're like, well, but it's infinity over infinity, do L'Hopital's rule a couple of times, and the top will stay infinity, and the bottom will end up getting to a constant. So because of this fun fact, we know that we must have c equals 0. So now we can come back over here and go back to black. And so therefore we get that capital Y of s equals 1 over s cubed. So now the last thing to do is take the inverse transform. So let's pull up our table of transforms again. Here we go. We don't need that fun fact anymore right now. So now we can look at, kind of go over here. There we go. Which one are we going to need? Well, we've got, it looks like we'll need something like that with, say, an n equals 2. So if we have the Laplace inverse, or the Laplace of t squared equals 2 over s cubed. So that means that if we get rid of that 2 over there, we get Laplace of t squared over 2 equals 1 over s cubed. And so that means that the Laplace inverse of 1 over s cubed equals t squared over 2, which is exactly what we're looking for. So now we get that little y of t equals the Laplace inverse of capital Y of s equals the Laplace inverse of 1 over s cubed, which equals t squared over 2. And this is exactly our answer, and you can verify by plugging in to the original ODE. Okay, so we wouldn't have been able to solve this problem using any of the other methods that we've seen so far, and that's where the Laplace transform is going to prove really useful to us. There's one more sort of section in the chapter that's kind of an example to engineering, and I'm not going to go through it, but I think it'd be valuable to read through it yourself, and I might assign a homework problem or two from related to that section. So if you see that in the homework, just read the chapter. All right, have a good one.